Okie doke. So this is the last lecture in the lecture course on the Standard Model. And we've covered now many of the conceptual aspects of the structure of the Standard Model. We've covered some of the more practical ones, things like the Feynman rules in unitary gauge and things like this in the electroweak sector, and spontaneous symmetry breaking, where we did an example with U1, but then did work through the full SU2 story. And we've even gone as far as in the last lecture to consider the low energy properties of QCD, which I consider to be tremendously important and foundational, really, for understanding the questions that are hidden within the Standard Model themselves. And so in this last lecture, I want to take the opportunity to sort of look beyond, because once you study the Standard Model, as we have done in these lectures, as with most things, there's a sort of a threshold where you start to grasp the basic concepts. And then there's another threshold where you feel comfortable with it. I hope you're close to that threshold, but I think probably it will take a little while for things to bed in, and you might need to perform some calculations, do the homework exercises and so on before you're at that point. But then once you're familiar enough with the Standard Model and the way it works, and also a little bit with the way quantum field theories work, that really reveals to us, once you understand it well, the problems, right? And it usually takes a while with any theory to understand it well enough to sort of see where the issues are. And there are issues within the Standard Model. And these issues and puzzles, problems, really compel us to look beyond the Standard Model. There are questions within the Standard Model that cannot be answered within the Standard Model itself. So it cannot furnish us with an answer to these questions, but nonetheless, these questions remain. And so today in this last lecture, I want to take the opportunity to discuss, I'd say, 2.5 of these questions, if I get time, if I stick to my own schedule. The first puzzle, which I think is a puzzle that follows very naturally from the material we studied yesterday, is the strong CP problem. The second puzzle is the hierarchy problem, or puzzle. And both of these are to a certain extent qualitative. There's no strict numbers you can put to them, but they're qualitative and they're to do with the structure of the Standard Model. There are some puzzles like, for example, the origin of the matter-antimatter symmetry, where we've got a number that we should be able to match, and the Standard Model doesn't match it, and that would really be those sorts of problems, and there are a few of them, are really quantitative problems within the Standard Model. But then there are the sort of qualitative, more structural ones, which are still problems nonetheless, but they're not associated with any sort of particular specific number or prediction. And then in the last few minutes of the lecture, I will discuss a little bit about dark matter. You will have lectures involving dark matter in the astro section, I believe. So I'm not going to dwell on it for long, but I just want to give a slight sort of particle physics-based perspective on that. Okay, so let's carry on. So this is just a little selection of puzzles. The first puzzle I want to discuss is the strong CP problem, which I think you're now well equipped, at least conceptually, to understand. And the strong CP problem has been around for a long time, and it concerns the QCD sector. And so there's a term which we've already discussed, and I alluded to this problem actually very early on in the lectures when we were thinking about the different type of terms in the Lagrangian, otherwise known as operators, that one could consider. And there's one in particular that's very interesting. I'll call it L, which has the strong couplings constant squared over 32 pi squared. And then some parameter that I will call theta. And then G mu nu, which is the gluon field strength, which we have constructed in the past. And then G mu nu tilde. And this is the CP odd field strength. So this is the field strength we've constructed before. And if you recall, we could contract that with the fully antisymmetric 4-index tensor, the Lorentz indices, to create something. So that's just a different rearrangement with different minus signs in front of different terms of the same field strength. And we can construct something which is CP odd. So under a CP transformation, it goes to minus itself. This is CP even. So this whole object here goes to minus itself under a CP transformation, which means that this theta parameter here is non-zero. Then this whole thing flips sign under a CP transformation, which means that the Lagrangian would not be invariant under CP. So this thing is a CP, we call it a CP odd operator. There's a whole interesting story about this operator. I'm not going to be able to go into it in too much detail. You may read in some places that this is a total derivative, and it is a total derivative. And that means that if you do any scattering process in perturbation theory, you will never find an effect that depends on theta. You'll have terms, there's interaction terms in here, and you can write them down, write down the Feynman rules, but ultimately, when you calculate any scattering amplitude, anything involving theta will cancel out. And so one might argue that then this term here, although it's CP odd, it's completely irrelevant because it has no physical impact. But it turns out that that is not the case, and it is relevant because there's more to life than perturbation theory. And in the standard model, there are effects that have nothing to do with perturbation theory. There's no perturbative calculation one could do to extract these effects, and they are known as non-perturbative effects. And we discussed them already in the past, probably in lecture 3 or something like that. Okay. So we will also recall that this term is exactly the sort of term that corresponded to an anomalous U1 symmetry in the quark sector. And so we can actually get rid of it. We can use the anomaly. We can use the fact that the path integral measure does not remain invariant under a U1 rotation of the quarks to actually remove this term from here. But because of that anomaly, we can remove it from here, but it will show up somewhere else. It's like whack-a-mole. Anytime you hit the, I don't know what it is, like a chipmunk or something like this, or mole, yes, whack the mole, and every time you get it down, it will pop up somewhere else. And that's exactly what happens with this theory. You can never get rid of it. Which means it is physical. We can't do a transformation that completely eliminates it from the Lagrangian or the path integral. But it will show up somewhere else. And one rotation, this is all quite schematic. One rotation you could do is, sorry, turn my lights on. It's maybe a bit better. One rotation you could do is to rotate the quarks by a phase. So I recall it would be something like, if say we just rotated the one of the two Weyl fermions by e to the minus 2I theta q. Then we would get that the whole path integral. So this is over all of the phi's, all of the fields. So let's just call it q and q bar. E to the I over h bar integral over d4x. The Lagrangian at with theta equals 0 plus this term gs squared over 32 pi squared theta g dual will get changed if this is the Lagrangian without this term and without any theta terms in the quark masses plus this term here. If I do this rotation, this whole object, the whole path integral will go from there to something similar but not the same. E to the I over h bar integral of d4x L of theta, where in L of theta, all that has happened is that the kinetic terms have remained the same, but the quark masses will have changed. And you can see, you can do this exercise yourself to see how much they change by when we do this transformation here. We will get something like, or sorry, that was just theta, I think no 2, just I theta. M q bar plus summation conjugate, this was the quark mass term, goes to e to the I theta q bar plus summation conjugate. So something has changed. This is this whack-a-mole thing I was talking about. We've gotten rid of this term. It's no longer in here. But we couldn't get rid of theta entirely. Theta then just showed up somewhere else, and that showed up as a phase of the quark masses. Now, these two theories are physically the same because field redefinitions, like doing a rotation or something like that, doesn't change the physics, even if it isn't a symmetry of the theory. If we do a rotation, field redefinition, the physical predictions of the theory have to remain the same. So these two theories are the same theory. Mathematically, they look different. There are different equations, but every single physical observable you calculate with either of these theories will be identically the same, and that's a theorem essentially. Okay, so let's work with it in this format here, and we can see that there is still a CP violating parameter, this plus Hermitian conjugate. This whole term here breaks CP if theta is non-zero. It's just a little bit less explicit than the way you see it here. Okay, so let's go back to what we learned in the last lecture, right? So when the quarks condense, we get pi mesons, whose properties depend on the mass term. If you recall, it was actually the quark mass term was precisely what led to the pion masses in the first place. But there are also other properties that depend on that term. It's not just the mass, but it's the entire potential and also some of the interactions between pions and other particles. And indeed, when you have this term in here, in the quark masses, let me circle it. When you have this term in here, you can then do the procedure that we did before, where we let the quarks condense and study the properties of the Goldstone bosons, which are the pion masses. And we can carry around this phase in the mass in those terms the whole time. And if we do that, we can then take that Lagrangian, which is the low energy effective theory, the IR theory, involving no longer quarks and gluons, but pions and rho mesons and neutrons and protons and things like that. And we can go ahead and calculate. And if we do this calculation, something interesting happens. So we can calculate, for example, all sorts of things. But one of the interesting examples, mumbling a bit, is the neutron electric dipole moment. So you can calculate final diagrams in this low energy theory that look like this. You've got a proton in here, and then like a loop of charged pions coupling to a photon. Because the neutron itself is electromagnetically neutral. It does not interact directly with the photon. It does not transform under QED, under the U1 symmetry of QED. But nonetheless, it can have interactions with photons via diagrams involving things like pi mesons. There's a proton, so this whole thing is neutral. And it turns out that this phase in here actually shows up in places like the interactions between a neutron, a proton, and a charged pion. There are also other diagrams that are important, involving, for instance, neutron. The neutron again, I think, the neutron, and then things like the eta prime meson. The eta prime was this meson that I mentioned before. Sorry, the phase shows up in here. The eta prime was this meson that I mentioned before, which was at the heart of this sort of controversy about whether or not there should have been an extra Goldstone boson, because it seems at the level of the classical Lagrangian, but not at the level of the path integral, that there was an extra symmetry, a U1 symmetry, that was spontaneously broken when the quarks condense, and there should be a meson. But QCD is anomalous under that. So that symmetry is anomalous under QCD. And so that the full quantum theory has no obligation to respect that symmetry. And so it has no obligation to spit out a Goldstone boson, which is why the eta prime is heavy. So it also plays a role in here. And then when you add them all up, you get contributions that look something like, neutron bar, sigma mu nu, neutron, F mu nu. By the way, I'm working in terms of two component file spinners, so let me not call it Q bar, let me call it QC, actually. But here I'm working in terms of the neutron EDM, because neutron is Dirac, looks like this in terms of Dirac spinners. So I probably shouldn't have written that operator down. Anyway, it's an electric dipole moment for the neutron. All right. And we can measure things like dipole moments. And in fact, it's not so easy to get a whole bunch of neutrons in the same place, but it's not impossible. And so you can put a whole bunch of neutrons in the same place and then simply apply electromagnetic fields in different configurations and extract, using spectroscopy and things like this, the interaction energy between the neutrons and photons, and then from that extract things like the magnetic dipole moments and the electric dipole moments, so how the thing couples to the electric field in a CP odd way. And these experiments have been performed for decades, actually. I think more than 4 decades. And no neutron EDM has been observed, and that limits the magnitude of theta to be less than something, I can't remember the precise number, but it's in this normalization, but it's in the ballpark of something like 10 to the minus 11. Okay. So why is that a puzzle? Why is such a small value of theta a puzzle? Well, if CP were a symmetry of nature, that would not be a puzzle at all, because we would just say, well, of course it's 0, because that's one of the symmetries. And for one thorn in our stone in our shoe, that would be a perfectly acceptable explanation. However, we've already seen in the quark masses that in the quark sector that there is a CP violating phase, right, which is the phase in the CKM matrix, which is being measured. It's non-zero. So the quark sector, the quark mass matrix itself, when you go to the full-blown theory with all the flavors, does not respect CP. Yet for some reason, this peculiar combination, and you can call it this phase here in front of this term here, or you can completely equivalently call it this phase here. It's exactly the same statement. So no matter where you shuffle it around, play your game of whack-a-mole, it's always there. And so yet there's this sort of, let's call it a diagonal phase or axial phase in the strong sector is something like 11 orders of magnitude or 10 orders of magnitude smaller than some off-diagonal phase in the quark sector. And there's no reason for that. There's really no symmetry that we can use to then enforce that. And so there's this puzzle, because if the standard model is UV completed by something else at higher energies, then why on earth does that UV completion spit out an off-diagonal phase that's sort of an order 1-ish number that can be measured, yet for some reason it is completely allergic to having a phase in the sort of diagonal phase like this in the quark sector. Now, there are some potential explanations. There are ways you can remedy this, or explain it. So one interesting thing is within the theory itself, that other phase in the CKM matrix does not feed in very efficiently to things like the neutron EDM. It does at some very high loop order. But so that phase itself is not a problem. It's not, it does not give you a contribution to the neutron EDM that's too big or something like that. We don't have to cancel anything off. And so one can concoct models in the UV, so at short distances, which take over from the standard model at higher energies, in which this sort of happens by sort of a happy accident in some sense, or because certain particles don't interact with each other, and there are various mechanisms to do that. However, an equivalent, or sorry, a more interesting idea, which was really pioneered by Petche, Quinn, and then Weinberg and Wilczek, relates to the axiom, which you may have heard of. And when we think about the axiom, we just promote theta is no longer just theta, but we essentially, and there are ways to do this, it's not something that's particularly exotic from the perspective of quantum field theories. Theta also gets a contribution from some dynamical field, scalar field, I'll call it little a here, divided by f, where f is some dimensionful parameter that has the same units as the field. So this whole thing is dimensionless. And this a is really a scalar field. It depends on the space-time, background space-time. So theta was just some parameter, it's just some number, but a is a field. It's really a, open parenthesis, open brackets, space-time coordinates, close brackets. Okay, and then we can essentially, there are some details, some slight details that change, but we can essentially do this rotation again, whereas now we rotate by something that's proportional to theta plus a over f. And then this, what we get is theta plus a over f in here, all gets cancelled. And in here we get theta plus a over f, which means that in here we will now get theta plus a over f as a phase in the quark mass matrix. Okay, and then what happens? So I'm going to be a bit sloppy here. Well, as I'm sure you can tell, I've been quite sloppy throughout the lectures in terms of factors of 2 and stuff like that, because I've been really trying to focus on getting the concepts across. But I'm going to be a little bit sloppy here and recall that you know, Q, the quark condensate, was something like scale like something G star, which is some coupling in the UV theory. This is below the QCD scale, so this is sort of like the QCD strong coupling times F pi cubed. So that was the quark condensate. So we can actually just plug this in here and calculate what happens. And we see if we say that G star F pi is of order m proton, which it sort of is, then the scalar potential that you get from this, so you take this, and this just becomes a number. So you've got a number times e to the I theta plus a over f, plus the Hermitian conjugate. And we know that e to the I theta plus e to the minus I theta is just essentially cosine. So we get V is essentially, that's the quark mass, and I'll just call it V0 minus V0, because this is the Lagrangian. So the Lagrangian has a minus V in it. V equals minus V0 cosine of theta plus a over f, where V0 is something like, you know, m quark, m proton, f pi squared. Okay. Which is of order something like 100 MeV to the 4. Okay, very good. So let's plot this potential. So now this scalar field, it can change, right? Because it's a scalar field, it can roll down slopes and things like this. So what happens to this scalar field? Well, we can plot the potential. Try and do it a bit better than that. Didn't succeed. We can plot the scalar potential as a function of a over f. And it will just be some cosine form with a shift of order theta. So this is V a over f. Down here, it'll be something like pi minus theta. And so on. 3 pi minus theta and so on. And so we see that if the scalar field, even if you started with the value like sat up here, it would roll down the slope, and it might oscillate around a bit, and this is exactly what would have happened in the early universe, for instance, but it will come to settle at this point here, where a over f is equal to pi minus theta. So it exactly cancels the theta term, or sorry, this is just theta minus theta. Because I've got the minus sign out here, which is the pi. Yeah, so it exactly cancels a over f, exactly once the scalar field A, which is the axion, goes to the bottom of its scalar potential, it is exactly cancelling the strong CP angle, this theta term, in that minimum, which is really, I think, a very beautiful idea. This was, so the relation of using this U1 symmetry is attributed to Peche and Quinn, Roberto Peche and Helen Quinn, and then it was Weinberg and Wilczek who pointed out that there would be actually a scalar field associated with this, which is the axion. And so dynamically, the axion would roll down to the bottom of its potential and cancel off the strong CP angle, thus cancelling off things like the neutron EDM. So you'd be predicting a vanishing neutron EDM. And then we can even calculate the mass from this. So the mass is just v double prime d2v by dA squared, where A is the scalar field. And we get that v double prime is m axion squared, which is essentially v0 over f squared. And so from this, we can extract that the axion mass is something like 10 to the minus 12 GeV, whenever f axion is around 10 to the 10 GeV. So it scales inversely with f axion. I'm sorry, this is not so clear to read. So the scalar field, if f is large, if that the axion decay constant, as we call it, which is just this parameter f, if it is very large, then the axion is very light. So if it were of order like 10 GeV, 10 to 10 GeV or something like that, then the scalar field would be lighter than an electron volt. So we have this sort of problem that's looking towards the UV, looking towards the highest energies and the shortest distance scales. And this solution spits something out at the other end. This solution spits something out in the deep IR, ultralight new physics. Now, why do I say 10 to 10 GeV? The reason for that is actually because the axion has interactions that scale like A over F everywhere. And that means that we can actually, but it's also very light. And when something is light, it can be produced very easily. And now the center of stars have stuff going on where the characteristic temperature or energy scale is like at the key keV scale, or even 10 keV. So it can abundantly, happily produce things that are lighter than a few keV. In supernova, even further, the energy scales are around, an MeV or even 10 MeV. So they can even produce particles that are lighter than those energy scales. However, stars are big. There are lots of particles colliding with each other in stars. And so even if something is extremely weakly coupled, so if this F is a huge number, which suppresses these interactions, still it can abundantly produce these particles. And so we have to keep dialing up F until the axion isn't, radically changing the predictions for the properties of stars. Even our sun can be used to place limits on the axion decay constant F. And what essentially happens is that the star we would produce, we've got a star like the sun, like this, and some hot core in here, and it would just be spitting out axions. And if the axion is weakly coupled, it could just escape from the star unhindered and then stream out. And that is a way of removing heat from the star, because stars, sort of the heat transport goes out to the surface, and then at the surface there's radiation, and that's how they lose their heat. Whereas this is a volume effect, because you can lose heat from the core because it can just be spat straight out in the form of an axion. And what that means is that gives it an additional significant source of heat loss and energy loss, which would then change the properties of stars. And that typically means, when you look at all these constraints, that typically means that F axion cannot be much less than around the sort of the 10 to the 10 GeV ballpark. Okay. So that was one example where we started to look beyond the standard model, and it used an observation about the structure of the standard model that cannot be explained within the standard model itself. It cannot answer. You can't answer why. The standard model can't answer why its own parameters take the values that they do. You have to look beyond to answer those questions. And the strong CP problem is a sort of a driving problem in particle physics. And indeed, it has really had a bit of a renaissance in recent years. More and more theorists are thinking about it, and more experimentalists are thinking about new experiments to search for the axion. There's really been a wealth of developments on the experimental front in recent years. And so if you're embarking on your PhD in particle physics, it's very possible that you may end up thinking about the physics of axions and how you might detect them. And if you do, I hope this sort of provides a bit of a particle physicsy field theory foundation for that. In fact, I think it's very useful to understand where the axion mass, for instance, comes from. And then, as you see, it's a very trivial calculation, essentially. I left out some details, but they're really just details. Okay. So next I want to move on to what I consider, and this is just a matter of taste, so you can disagree, your supervisors could disagree, that's fine, but a problem that I consider to be essentially the biggest problem that the standard model is facing, because it is one that cannot be arbitrarily hidden away. You see, we can make this axion more and more weakly coupled, and it can become harder and harder to discover it. We can, of course, chase it down and try and close all the loopholes, but it's not something that we can arbitrarily, it is something that we can almost arbitrarily hide away. But the hierarchy problem is of the opposite nature, and the reason for that is the LHC. So I'm not far from CERN at the minute, and the LHC is running around in, under these fields over here. And it has really put the hierarchy problem under immense focus, almost so much focus now that some folks, I think, are even scared of working on it or talking about it, because it's become such a hard problem to solve. So this is something that is really staring us in the face. Okay, so let's recall the pions and QCD. So if you recall this structure, we had the UV completion, which was the standard model, with things like quarks and antiquarks and gluons. That says the UV completion. And then we had the IR theory, we call it the effective theory. And that contained things like pions, quarks, kaons, protons, neutrons, and so on. Now, in principle, in practice, it's for the most part true, but there are computational limitations. But in principle, you can derive all of the properties of the IR theory from the UV. And we saw in the last lecture how to do that, how to sort of estimate the size of the pion masses and things from the quark masses. So that's UV is the quark masses. And the quark masses in the scale at which dimensional transmutation occurs and the strong interactions become too strong. And we can use that to derive parameters like the pion mass, which themselves within the IR theory, if you only had access to the IR theory, are purely empirical parameters, purely parameters that you can only measure and not explain within the IR theory itself. Of course, there were no big surprises if we understand field theory enough. There was spontaneous symmetry breaking because of quark condensation. The pions would have been massless as a result of that spontaneous symmetry breaking in Goldstone's theorem, were there not some explicit breaking of the continuous global symmetry in that UV theory. And that explicit breaking was the quark masses, and we could estimate the pion mass from the quark masses and essentially the proton mass, and everything worked out well. But there was another little detail that I did hide from you, which is also, it just goes further to confirm the intuition for how these things work. And that was to do with the charged pions. So the kinetic terms themselves for the pions don't have the quark masses in them. And the neutral pion, the kinetic term at leading order, just has a standard shift symmetry. So that involves no symmetry breaking at all, which this part at least then would convince you that you don't generate any, you shouldn't expect from the UV to have any pion mass being generated from these sorts of terms, because there's no quark mass in there, which explicitly broke the symmetry. But when we get to the charged pion masses, it's a completely different story. So remember, this covariant derivative was d mu plus I e in mu. And this breaks any shift symmetry on pi plus. If I do pi plus goes to pi plus some constant, the derivative hits that constant and gets rid of it. So there's a shift symmetry there. But this gauge field, the photon does not. And that's in contrast to the neutral pions. So just playing by the same old rules, if we have some parameter in the IR theory or the UV theory, which is breaking explicitly the potential shift symmetry, so the global symmetry, then that we would expect would lead to corrections to masses. And indeed, that's precisely what happens. So you would expect, you would estimate that the charged pion masses are different mass squareds from the neutral pion mass squared by an amount that's proportional to, we have to get our dimensions correct. So E squared, because that's the gauge coupling squared. Then an H bar turns that into a dimensionless quantity. 4 pi squared, because wherever we get an H bar, we usually get a loop factor. And then something like a mass scale squared. The only mass scale in the UV theory here is the QCD scale, so like around the proton mass or the rho mass, the rho meson mass. It doesn't, at the level of accuracy we're working, it doesn't matter so much. So just from looking within the IR theory, we have this big explicit breaking of any shift symmetry for the charged pions as a result of their gauge interactions. And that means that in the UV theory, there's some breaking which corresponds to that gauge interaction. And so there's no way to forbid mass corrections if we were to do this, deriving the properties going from the UV to the IR, because of the gauge couplings as well as the quark masses. There's no way to forbid corrections to the pion masses because they're not protected anymore by Goldstone's theorem. You can estimate them to be of this scale, and this is precisely what happens. You can measure the difference between the charged and neutral pion mass squares, and you get something that scales perfectly like this. And you can even go ahead and do this calculation going from the UV to the IR and calculate it, and you get the right answer really well, actually. So this shows us that there's a rule of thumb. These notions about going from the UV to the IR, they're the sort of typical rule of thumb where if you see some symmetry breaking, some shift symmetry breaking, for instance, for a scalar, then you would expect whatever the UV completion is, the UV completion has a very concrete meaning. It's the thing that explains the microscopic origins of the IR theory that you're studying. If there's a parameter like that, then it will feed into the mass squared of the scalars if any potential shift symmetry is broken. And the dimensional field parameter that gives you the estimate for the mass that shows up depends on the mass scale of the UV completion. So now let's consider the standard model. So we consider the standard model, then we have exactly the same picture. We know the standard model isn't complete. We know it will break down at some scale. And so we have some UV completion, and we don't know what it is. There must be the UV completion of the standard model. So up here, we've got some UV completion. Who knows? Big question mark. Down here, we've got the standard model. And it contains things like the Higgs, the W bosons, the quarks, leptons, and so on. So that's all down here. And whatever that UV completion is, we would expect to be able to derive the properties of the IR effective theory from it. Now, the IR effective theory does break down at some energy scale, so we can't ignore this fact. We can't just explain it away by saying, well, I don't like that. That's simply not an option. So there will be some UV completion of the standard model. And we expect to be able to derive the properties of the standard model from within that UV theory going down into the IR theory, which is the standard model. But just like the pions, the Higgs has interactions which break any putative shift symmetry. And in fact, those interactions, the gauge interactions, are entirely analogous to the story for the pions. They're the shift breaking interactions that we see in the IR theory already, so there must also be breaking in the UV theory. Are, for instance, the gauge interactions. This is completely analogous to the charged pion shift symmetry breaking. But also for the standard model Higgs, we also have the Euclid interactions, things like QUC, Higgs QUC, etc. So this means that following the same rule of thumb, you should expect corrections to Higgs mass that go like h bar, for example, g squared, where that's the electroweak interaction, 4 pi squared, and then MUV squared, whatever that scale is. And also the ones from this that are going like, there's 3 tops, so let's stick in 3. Lambda top squared over 4 pi squared, MUV squared. And so we expect that, and this is, this thing here, these are completely analogous to the pions, but this is really very directly analogous to the pions. And we saw that this is precisely what happened for the pions. So this is not like ultra speculative idea. I mean, this is literally what we've seen in nature. And also we've not only seen it in pions, we see this same thing occurring, for example, in condensed matter systems and so on. So this isn't by no means speculative. And so reversing this, that we see that we expect that the UV scale must be less than something like, we reverse this one, it's even more stringent, something like 4 pi over root 3 h bar lambda top, and then m Higgs, where that is what we observe, so something like 125 GeV. And then that tells you here that we expect MUV to be less than something like 800 GeV or so. I put in or so. The or so is important because there are caveats, little caveats, not big ones. And so the hierarchy problem is, well, okay, fine. Where is everybody? All right, where are all these? Where is the UV completion? Why haven't we seen it yet? And this is a big issue, and it has led to a lot of head scratching. Where is everybody? Is the big question. Okay, so how can we address this? Now one could be like a climate denier or an anti-vaxxer and just say, well, I'm not going to tell you what's happening, but I don't believe there's a problem. But that's not science. That's really the opposite of science. That's just deciding that you don't want to discuss something, and because you're uncomfortable about it. Otherwise, we have to explain this puzzle. Now, one could say that, well, perhaps there are quantum field theories where the UV completion has symmetry breaking, like, shift symmetry breaking, like these gauge couplings and things and so on. But when you go to the IR, this does not give a correction to this does not feed into the Higgs mass squared. And so maybe there isn't a problem. But then you see the onus, the obligation on the part of the theorist or anybody interested in this problem is to give an example. Okay, so it doesn't even have to work for the standard model, but an example of a theory where that happens, where you can have a light scalar which doesn't get these mass corrections, but still has things like Eucala interactions and gauge interactions in the IR theory. One cannot simply say, well, I believe there's a theory, but I'm not going to tell you what, because I'm not going to do the work. That's philosophy. That's not that's really mean on philosophy. I'm a big fan of philosophy. That's worse than that's just not science or philosophy or anything. And so one is obliged then to show how that works, to give examples. And we only really have one working example that does that. Of course, there may be other theories that we haven't discovered yet, and that's why we have to work on understanding theories, and that's why it's very important that certain theorists spend a lot of time understanding the structure of quantum field theories, even if they don't have direct application to the standard model or to the physics that we do with experiments, because we need to understand what a quantum field theory is better, because there could be explanations for these big physical problems that we can't yet answer, but we may be able to if we understand quantum field theories a bit better. So that's great. But in terms of the progress that's been made, there's only really been two types of theories that have been discovered that can have this property and can explain the Higgs being light. The first is really to take the Higgs to be like a pion, and this is called composite Higgs models. So in composite Higgs models, the Higgs is really like a pion. There's there would be in the UV theory some sort of quark condensation, but also some global symmetries that are spontaneously broken, and giving rise to light scalars in the IR theory that one can associate with the Higgs boson. And these theories make a bunch of interesting predictions. So the first is you do get mass corrections that scale in this way within those theories. And so it's very much analogous to the pions of QCD. And then that means that you cannot, because of these simple facts, you cannot get the UV completion to go too high, too far up. MUV, which in this case would be something like the analogous particle to, for example, the rho meson, which is a vector meson in the Standard Model. MUV cannot be too high, so you do indeed expect vector mesons to show up with masses at around like 800 GeV, or because it's just electroweak, this coupling is a bit smaller, so you can tolerate heavier up to like a couple of TeV or something like that. But we should see them ultimately, whether it's at the LHC or some higher energy collider. But furthermore, if you recall, the decay constant of the pion, F pi, was in a theory that's strongly coupled like QCD, was actually quite close in the end of the day to the pion masses. And that relates to the scale of the quark masses and things like this. But also we can extract the rho meson masses from this notion that F pi was like m rho meson or m proton, the same mass scale, the mass scale of QCD, divided by the strong coupling. And so when the strong coupling was about 4 pi, there was only about a factor of 4 pi that you could have between the decay constant and the scale of the UV completion. But then there's a bit of a problem, because that naturally, if we want the rho mesons to be heavy enough that we haven't seen them yet at the LHC, that means that the decay constant itself wants to be, 4 pi between the mass squares. It wants to be like around sort of 700 or 800 GeV, not sort of 174 GeV, which is what we have for the Higgs. And so one has to, in the scalar potential, one has to start to fine tune parameters to get the decay, the Higgs VEV, to not be at like 700 or 800 GeV. And so one has to do a bit of fine tuning. There's another aspect, which is that the Higgs couplings, this is an aspect that's also related now really to LHC observations, which is that the Higgs couplings in a theory like this would be modified by a factor that goes like V squared over F squared. And so the Higgs couplings have been measured to be very Standard Model-like, to the level, in some cases, of about 10%. And that means V squared over F squared has to be less than about 0.1. And so we want F to be big because of the Higgs couplings. And nonetheless, in the scalar potential, when you add up all these sorts of corrections, you find that F wants to be at the same, V and F want to be at the same sort of scale. So there's a bit of fine tuning already in composite Higgs models. So they're a great approach to the hierarchy problem. And I think, in my mind, the most obvious approach to the hierarchy problem, because it simply repeats essentially a story that we've already seen in nature in the QCD sector and the pion sector. On the other hand, these theories are under a lot of pressure from fine tuning. So it's starting to be a bit of a question as to whether or not they really are solving the problem. Of course, they do solve it up to very high scales. Then the next scale of UV completion could be unbelievably high. But we're starting to have a problem at lower scales that we're calling the little hierarchy problem, which is the where is everybody after the LHC problem. The other example is supersymmetry. So supersymmetry forbids big corrections. So supersymmetry is an example of a theory, and it's the only one I know of, where you can have things like Yukawa and gauge interactions in the theory, but when you go to low energies, you do not retain any sensitivity to these mass scales. So these sorts of corrections are absent, and they're forbidden by supersymmetry. And that's why it's such a beautiful, well, there's many reasons that supersymmetry is so beautiful. But the Standard Model itself is not supersymmetric. As you recall right at the start, if one has a symmetry, then the fields of the particles should fill out representations of that symmetry. So if you have SU3, there should be a vector of 3 fields that the SU3 matrix can act on. And it's exactly the same, well, it's not exactly the same, but it's very much similar for supersymmetry, where one has to have representations, fields filling out, representations of supersymmetry. And to do that, the symmetry requires the existence of additional fields. There are scalar fields that partner up with the fermions, fermionic fields that partner up with the scalars, and so on. I'm sure you're familiar with the story. And so these new particles have to be there by dint of the symmetry. They have to fill out the representations. And they haven't shown up yet either. It could be that they are at higher mass scales, but whenever you don't have supersymmetry, you can't escape these sorts of corrections, because it was supersymmetry that was getting rid of them. So if we have supersymmetry at high energies, but then get rid of supersymmetry, you know, the universe becomes not supersymmetric at, for instance, the TeV scale, then we've no longer got that protection from the TeV scale down to the electroweak scale. So at the point where that protection is lost, these things come back. And so we've got the same old problem that these new particles, the new supersymmetric particles, feed in as essentially as the effective scale of UV completion, because that's the scale at which the protection from supersymmetry is lost. And so you expect them to show up at, you know, by sort of 700 or 800 GeV, or maybe even 400 GeV, depending on how much sort of baroqueness of model you can tolerate. And they've not shown up yet at the LHC. And so there's a big puzzle there. And so that really takes us to the end of, I thought I might do a few minutes on dark matter, but I'm not going to, because I'm really running right to the end of the lectures. But if I put up my handwritten notes online, maybe you can have a look at it there. Okay, so that really concludes the standard model lecture course. We've sort of plowed through a lot of technicalities. I'm sure some of my equations have been a bit sloppy, so I apologize if I made any mistakes in any of them. And so we've gone through some technicalities, but hopefully, you know, really, I believe the most important take-home message is really the conceptual aspects that we've discussed, the aspects relating to gauge symmetries and UV completions and the IR theories, and the connection between the physics of pions and quarks and gluons in QCD, things like the Higgs mechanism for spontaneously broken gauge symmetries, and so on and so on. And in this last lecture, I sort of given you a little bit of a taste about the questions that we ask about the structure of the standard model and some of the answers that are proposed. That relates to some things that you may hear about in your PhD searches for supersymmetry or axions and things like this. I should say as well, you know, we're really at a new frontier at the moment in terms of particle physics. Things have changed a lot. You know, in the 90s and the first decade of this millennium, I believe, you know, there was some anticipation that we sort of were maybe on the right track already to understanding what this story of the UV completion was going to be. And many people expected, for instance, supersymmetry or composite Higgs scenarios to be discovered at the LHC. And the fact that that hasn't shown up has really been shaken the earth under our feet. And so really high energy physics at the moment is like the final frontier. I've been rewatching some old Star Trek movies recently, and I sort of feel like this quote, you know, that comes up at the start, you know, that regarding the final frontier and the mission of everyone on the you're probably not fans of Star Trek, so I shouldn't go into it too much. But anyway, you know, there's this quote about the final frontier, and your mission is to, you know, explore strange new worlds. I think in particle physics, then we would say, and seek out new particles and laws of nature. And at present, we really have to be creative and boldly go where no physicist or scientist has gone before, if we're going to answer these questions, which we are obliged to try to do. And so I hope that in your future studies and your research, you find ways with your supervisors and your collaborators to take us in new directions, because that's what we desperately need at the minute. I'll finish there.